Okay, a polynomial. Well, just as an example, what we have here is a sum of multiples of power functions. Okay, we have x to the fifth, that's just 1x to the fifth. And we have a negative 3x cubed, that's another, x cubed is another power function. Negative 3x cubed is a multiple of that. 1/2 x squared is a power function. 1/2 x squared is a multiple of a power function. X, which we write here just to be explicit, is x to the 1, but anytime you just see x, we understand that its exponent is 1, and it is a power function with p equal to 1. That means p equals 1, we have y equals x to the 1, it's a power function. Okay, so we have 7 of those, and then we have negative 4x to the 0. Okay, now of course x to the 0 is always 1. So if I just wrote this as negative 4, it would be the same as negative 4x to the 0. And usually we won't write the x to the 0, but sometimes to be explicit and maybe until we really understand that, we probably would do well to write, instead of just negative 4, write negative 4x to the 0, because of course that's negative 4 times 1. And we see then that that is a multiple of a power function, the power function x to the 0. The y equals x to the p function when p is 0. Okay, well, this then is a sum of multiples of power functions where all the powers are non-negative integers. You don't have any x to the 1/2, you don't have any x to the negative 2. Nothing negative, nothing but non-negative integers. And I say non-negative instead of positive because, of course, 0 is one of your non-negative integers, and we will need x to the 0. Okay? So that's just an example of a polynomial, and that's how we define a polynomial. That's what we mean by a polynomial. Now, I do make a statement here that's just kind of a statement for interest. As it turns out, this is actually called the fundamental theorem of algebra. It's a very big deal, and it was somewhat difficult to prove. A lot of abstract algebra had to be developed in order to prove this. But any polynomial can be expressed in this form: x minus a times x minus b times x minus c, and so forth. And actually, I kind of lied. Don't know what to put in front of this. I'll put a capital A, which is distinguished from the lowercase a. Okay, we need a coefficient out here because sometimes the highest power term has a coefficient other than 1, obviously. Okay, well, the point is that we can factor it like this. Now whether we can actually find the factors, that's our problem. But it does have factors of this form, just linear factors, with the catch that a, b, and c are complex numbers. Now that doesn't mean that they necessarily have a non-zero imaginary part, or for that matter, a non-zero real part. 5 is a perfectly good complex number. It's 5 plus 0i. We don't bother writing the 0i. 7i is a perfectly good complex number. We just don't bother writing the real part. It's 0 plus 7i. We don't write the 0. So, where a, b, c, and so forth are complex numbers, if we allow these to be complex numbers, then any polynomial, this one or any other one, can be expressed in this sort of a form. Now we'll talk more about this because we do want to talk a little bit about the fundamental theorem of algebra because it's kind of important. And there are other implications of this for the shapes of the graphs and just for the basic graphing of polynomials. But we'll get to that later. So what we want to see is, first of all, examples of the p equals 2, 3, 4, and 5 power functions. Okay? Then examples of, well, then what do the graphs look like? Definition of power functions, some things about the domain of the power functions, and the idea of a polynomial. And we'll build on that in the regular session class tomorrow.